Welcome back to the Deep Dive. Today we are attempting something that, quite frankly, feels a little bit like magic. We're going to try to explain how scientists can predict the future of materials, how they can design, say, a better battery, a stronger alloy, or a more efficient solar cell, without ever actually stepping into a laboratory.
It really does sound like magic, doesn't it? But it's actually just very, very heavy math.
Heavy math it basically runs the modern world. I'm talking about density functional theory, or DFT. And to guide us through this, we are looking at what is, well, arguably the Bible for beginners in this field. It's a classic textbook called Density Functional Theory, a practical introduction by David S. Sholl and Janice A. Steckel.
It is a classic for a reason. You know, a lot of physics textbooks are written by theoretical physicists for other theoretical physicists. They love the derivation, the elegance of the equations. But Sholl and Steckel wrote this for the people who actually need to, use the tool.
Exactly. And that is our focus today. We aren't going to derive the equations on a blackboard. We are going to learn how to use the tool. And the authors actually start with this fantastic analogy that I think just sets the tone for the entire deep dive. They compare learning DFT to learning how to drive a car.
It's the perfect analogy. I mean, think about it. When you get into your car to drive to the grocery store, you have a goal. You want to get from point A to point B.
Right.
And to do that, you need to know a few things. You need to know that the pedal on the right is the gas. The pedal on the left is the brake. You need to know the rules of the road. You need to know that you have to put fuel in the tank.
But, and this is the big but, you do not need to know how to machine a fuel injector out of a solid block of aluminum.
Precisely. You don't need to understand the thermodynamics of internal combustion or the fluid dynamics of the air intake to be a perfectly good driver. For a long time, quantum mechanics was a field where you really had to be a mechanic. You had to know how to build the engine from scratch. But DFT changed that. DFT is the user interface. It's the steering wheel and the dashboard. It allows chemists, material scientists, and engineers to drive the quantum mechanics car to discover new materials without needing to spend 10 years deriving theorems.
So today, we are going to learn to drive. We're going to go through this book chapter by chapter and see how this engine works, how to steer it, and importantly, how not to crash it into a tree.
And believe me, there are plenty of trees to hit if you aren't paying attention.
Let's start at the beginning.
Yeah.
Chapter 1, the quantum foundation. Before we even get to the solution DFT, we have to understand the problem. Why do we need this special theory? Why can't we just use the famous equations we already have? I mean, everyone knows the Schrödinger equation. APB size, it's on T-shirts, it's on coffee mugs. It looks so simple.
It is deceptively simple. Let's break that down. A psi equals EC. So Nollers is the Hamiltonian. That represents the total energy operator. Basically, it's a set of instructions that asks, what are all the forces acting on this system? Other is the energy, which is usually the number we're trying to find. And Chisi, that Greek letter, psi is the wave function.
A wave function. This is sort of the soul of the quantum system, right? That's how I think of it.
That is the very poetic way to put it, but yeah. The wave function contains absolutely everything there is to know about the system. If you know the wave function, you know where the electrons are likely to be, how fast they're moving, everything. So in theory, if you can solve that equation, you've solved the universe.
But here comes the many-body problem.
A many-body problem. This is the wall that physics slammed into in the early 20th century. You see, the Schrödinger equation is, well, easy is a strong word, but it's solvable if you have one electron. A hydrogen atom, piece of cake, we can solve that with pen and paper.
Right.
But as soon as you add a second electron, things get messy.
Because electrons are negatively charged, they push each other away.
Exactly, they repel each other. So electron A is moving, but its movement depends entirely on where electron B is. And electron B is moving, but its movement depends on where electron A is. They are coupled, they're correlated. You can't solve for one without solving for the other simultaneously.
And that's just 2 electrons.
That's just 2. Now imagine a real material. Let's say a tiny microscopic cluster of platinum atoms. Maybe 100 atoms. That is literally a speck of dust. But platinum has a lot of electrons. If you try to write down the wave function for that system, you are dealing with a mathematical function that lives in, wait for it, 23,000 dimensions.
23,000 dimensions. My brain hurts just trying to visualize 4 dimensions. What does that even mean?
It means that to specify the state of the system, you'd need a list of 23,000 numbers. It's mathematically impossible to solve by brute force. If you use the fastest supercomputer on Earth and tried to solve the full Schrödinger equation for that tiny speck of platinum, you would be waiting until the heat death of the universe for the answer. It is just too much data.
So we were stuck. We had this beautiful, perfect equation, but we couldn't actually solve it for anything that really mattered.
Until the 1960s. This is when the density functional theory revolution began. Two physicists, Pierre Hohenberg and Walter Kohn, had a realization that effectively won them the Nobel Prize. They realized we were tracking the wrong thing.
We were looking at the dancers instead of the dance floor. Is that a good way to put it?
In a way, yes. A very good way. They asked, do we really need to track the 23,000 dimensional choreography of every single electron relative to every other electron? Or is there a simply quantity that holds the same information? And they found one, the electron density.
So instead of tracking the individual position of every single electron, we just sort of look at the crowd, like a blur.
Exactly. We call it 9R. It simply tells you how many electrons are in this tiny volume of space. It's like a heat map. A cloud. It's dense near the nucleus, and it fades out as you get further away.
And why is that better?
Because the electron density only has 3 coordinates, x, y, and z. It doesn't matter if you have 1 electron or a billion electrons. The density is always just a 3-dimensional function. You've collapsed a 23,000-dimensional monster down to a manageable 3-dimensional map.
That sounds like a massive, massive simplification. But usually when you simplify things that much, you lose information. If I take a high-resolution video of a crowd and just turn it into a heat map of where people are standing, I lose all the details of who is talking to whom.
That is what everyone thought. And that is precisely why the Hohenberg-Kohn theorems are so profound. They proved mathematically that you don't lose the critical information.
Okay, walk us through these theorems. Chapter 1 leans on them very heavily.
Theorem 1 is what I'd call the mapping theorem. It says that the ground state energy of a system is uniquely determined by its electron density. In other words, there is a one-to-one mapping. If you know the density, you implicitly know the wave function and you know the energy. The map is the territory.
Wow. So we aren't settling for a blurry picture. The density really does contain the answer.
Correct. And then comes Theorem 2, which gives us a way to find that density. It's a variational principle. It basically says that the true electron density, the one that nature actually chooses, is the one that minimizes the total energy.
Nature is lazy.
Nature is incredibly lazy. A ball rolls down a hill to minimize its potential energy. Atoms bond to minimize their chemical energy. Theorem 2 tells us, if you want to find the real electron density, just keep tweaking your guess until you find the one that gives the lowest possible energy.
Okay, so we have a map, the density, and we have a rule, minimize the energy.
Yep.
But we still have a problem, right? Electrons still repel each other. Even if we're just looking at the density, the physics of that repulsion must be really hard to calculate.
It is. The Hohenberg-Kohn theorems told us that a solution exists, but they didn't tell us how to calculate it practically. That is where the second big breakthrough happened. Walter Kohn again, this time with Lou-Sham. This gave us the Kohn-Sham equations.
This is the engine under the hood, then. When we run a DFT simulation, this is what the computer is actually solving.
Yes, and it relies on a brilliant trick. A Trojan horse, if you will. Kohn and Sham said the interacting electrons are too hard to calculate because they are all pushing on each other. So let's imagine a fake system.
A fake system.
System of non-interacting electrons. Imagine ghost electrons. They don't repel each other. They don't feel each other's presence at all. They just move through a background energy landscape. Because they don't interact, the math for them is incredibly easy. You can solve it for one ghost, then the next, and just add them all up.
But we don't care about ghost electrons. We want to know about real electrons.
And here is the magic. Kohn and Sham proved that you can design this fake system. Specifically, you can design the effective potential that the ghosts move through in such a way that the density of the ghosts is exactly the same as the density of the real interacting electrons.
Wait, hold on. Let me get this straight. We solved the easy problem for the ghosts to get their density.
Yeah.
And because their density is the same as the real system, we can then use Hohenberg-Kohn Theorem 1 to get the real energy.
Precisely. We get the right answer by solving the wrong but much, much easier problem. It is one of the most clever, intellectual sleight of hand tricks in the history of physics.
But there has to be a catch. There's always a catch. You can't just wish away all the complexity of electron repulsion. The bill has to come due somewhere.
You are absolutely right. The bill comes due in a single term called the exchange correlation functional, or ECF.
Exchange correlation functional? That sounds like the junk drawer of the theory.
Ideally, it's a neatly organized drawer, but yes, that's a good way to think about it. In the Kohn-Sham equations, we separate out everything we know how to calculate easily, the kinetic energy of the ghost, the electrostatic attraction to the nuclei, and then everything that is hard, the real electron repulsion, the quantum mechanical spin effects, the correlation effects, we just sweep all of that into this one box, EXT.
And do we know what EXT is? Like, is there an equation for it?
No.
No.
No. We know it exists, the theorems prove its existence, but we don't have an exact equation for it. If we did, DFT would be perfect, we would have God's view of chemistry, but we don't, so we have to approximate it.
And this is where the practical part of Sholl and Steckel's book really kicks in, isn't it? Because as a user, you have to choose your approximation. You have to choose your functional.
Choosing your functional is the single most important decision you make. The book highlights two main flavors of approximation. The first rungs on a ladder we'll talk about later, LDA and GGA.
Okay, let's break those down. LDA, local density approximation.
This is the simplest one imaginable. It assumes that at any tiny point in space, the electrons behave as if they were in a uniform electron gas. Imagine a vast, endless ocean of electrons that is perfectly flat and smooth. LDA looks at a point in your atom and says, okay, the density here is X. I will assume the energy contribution from exchange and correlation is the same as a uniform ocean with density X.
But atoms aren't uniform oceans. They have nuclei. They have empty space. The density changes rapidly from place to place.
It does. LDA is a very crude approximation. And because of that, it tends to overbind atoms. It predicts chemical bonds that are too short and too strong. But surprisingly, it works okay for simple metals. For most chemistry, though, it's not good enough. So we step up to GGA.
Generalized gradient approximation.
Gradient is just a fancy word for slope, or the rate of change. In LDA, I only look at the density value right at my feet. In GGA, I look at the density value at my feet, and I look at which way the hill is sloping. I know if the density is increasing or decreasing around me.
So you have a little bit more information about the local terrain.
Exactly, and that little bit of extra information makes a huge difference. GGA is the workhorse of modern material science. If you read a paper on battery materials or drug design or catalysis, chances are they used a GGA functional like PBE.
So to recap this whole engine segment, we have a guess for the density. We plug it into the Kohn-Sham equations using an approximation like GGA. We calculate the behavior of these ghost electrons. We get a new density out. And then we have to loop back.
The self-consistency loop? This is the core algorithm.
Guess the density. The computer usually just takes a wild guess to start, maybe by overlapping atomic densities.
Calculate the effective potential based on that guess.
Solve the Schrödinger-like equation for the ghosts in that potential.
Calculate the new density from the solutions for the ghosts. And step 5, compare. Does the new density match the old density?
And if it doesn't, which it won't on the first try,
you take the new density, maybe mix it a little with the old one to keep things stable, and you feed it right back into step 1. You rinse and repeat. You might do this 10 times or 100 times. Eventually, the input matches the output. The system stops changing. We say the calculation has converged.
And that converged state is nature's answer. That is the ground state, energy, and density.
That is the foundation. Now that we have the engine running, we need to build a world for it to drive in. This brings us to segment 2, Building Virtual Worlds, chapters 2 and 3 in the book.
Okay, so the book shifts gears here from, deep quantum theory to geometry. Because usually we aren't just simulating one atom in a vacuum. We want to simulate a solid, a crystal, like silicon or iron or diamond.
Right. And crystals present a unique problem. They are, for all practical purposes, infinite. A diamond is a repeating pattern of carbon atoms that goes on for billions and billions of rows. You can't type a billion atoms into your input file. Your computer would explode.
So how do we simulate infinity on a laptop?
We use a clever combination of a supercell and periodic boundary conditions.
The book uses a great visual for this, like a Pac-Man universe.
That is the perfect analogy. Think about the game Pac-Man. When Pac-Man runs off the right side of the screen, he doesn't hit a wall. He immediately reappears on the left side of the screen. The space wraps around.
So we define a small box, the supercell, that contains maybe just 2 or 8 atoms, the smallest repeating unit. And we tell the math, this box repeats infinitely in every direction.
Exactly. So if an electron flies out the right side of the box, it enters the left side of the neighboring box, which is just an identical copy of the first box. So the electron thinks it's traveling through an infinite crystal, even though we are only explicitly calculating a handful of atoms.
But there's a very practical question here. How big should that box be? I mean, atoms have a specific distance they like to be from each other, the bond length. If I make the box too small, I'm squishing the atoms together. If I make it too big, I'm stretching them apart.
And that is usually the very first calculation you do in any new project. You have to find the equilibrium lattice parameter. You run a series of calculations. First, you set the box size to, say, 3.0 angstroms. You run the code, it converges, and you get an energy. Then you set it to 3.1 angstroms, get the energy. Then 3.2, 3.3, and so on.
And because nature is lazy, you are looking for the minimum energy point in that series.
You plot those points on a graph. Energy versus box size. It usually forms a nice parabola, a U shape. The very bottom of that curve corresponds to the equilibrium lattice constant. That is the distance the atoms want to be apart. That's how we can predict the density of a material that doesn't even exist yet.
Now, there is a concept in Chapter 3 that I think intimidates a lot of beginners. The book spends a lot of time on it, for good reason. Reciprocal space or K-space?
Yes. K-space. It's kind of the gatekeeper concept.
Yeah.
If you can get your head around K-space, you can do solid-state DFT.
Why do we need it? Why can't we just say the electron is at position X? Why do we have to go into this weird alternate dimension?
Let's use an analogy. Think about music. You can describe a song in two different ways. You can look at the sound wave, the squiggly line that goes up and down over time. That's real space.
Okay.
Or you can look at the equalizer bars on your stereo, the bass, the midtones, the treble. That describes the song in terms of its component frequencies. That is reciprocal space.
Okay, so they're just two different ways of describing the same thing. One in time, one in frequency.
Yes. But here's the key. Crystals are periodic. They repeat, like a drum beat. When you are dealing with repeating patterns, which are fundamentally waves, it is often mathematically much, much easier to work in the frequency domain in reciprocal space than in real space.
So reciprocal space is basically a map of the periodicity or the waviness of the crystal.
Exactly. And just like we have a box in real space, the supercell, we have a corresponding box in reciprocal space. It's called the Brillouin zone.
The Brillouin zone. It sounds like something out of a sci-fi war movie.
It's just a mathematical box. But here's the practical part for a user. To calculate the total energy of the crystal, we effectively have to sum up the electron behavior everywhere inside this Brillouin zone. But we can't sum up an infinite number of points. So we take samples.
We overlay a grid on the box and just check the points on the grid.
Right. We pick a specific grid of points. These are the K points, and this is a major setting you, the user, have to choose. You have to tell the computer how many K points to use in its grid.
And I'm going to guess more is better.
More is more accurate, yes, but also more expensive. If you use a 1 by 1 by 1 grid, you're only sampling 1 point. It's like trying to judge a whole symphony by listening to one single half-second note. Your answer will almost certainly be wrong.
Right.
But as you add more points, a 3 by 3 by 3 grid, then a 5 by 5 by 5 grid, the cost goes up, the calculation takes longer.
So it's a trade-off. You need enough cobits to get the right answer, but you want to use few enough to finish the calculation before you retire.
This leads to the idea of convergence testing. You run the calculation with a 3 by 3 by 3 grid, write down the total energy, then you run it again with a 4 by 4 by 4 grid, write down the total energy, then 5 by 5 by 5. You watch the total energy. At first it will jump around, but eventually as the grid gets finer, the energy will settle down to a specific number. When it stops changing, you are converged with respect to your K points.
There is one more convergence parameter the book highlights, the cutoff energy, or ECUD-OCUD. This one seems related.
It is, yeah. This goes back to how we describe the shape of the electron density in wave functions. In most solid-state DFT codes, we use a set of plane waves. Basically just simple sine and cosine waves to draw them.
Like building a complex shape out of a bunch of simple Lego bricks.
That's a great way to put it. Or think of it like drawing a digital picture. If you want to draw a smooth, gentle hill, you can use a broad brush. That's a low-energy, low-frequency wave. But if you want to draw a sharp spike like the electron density right near the nucleus of an atom, you need a very fine point pen. You need high-frequency, high-energy waves.
And the cutoff energy determines how fine your pen is, how many of those high-frequency waves you include.
Exactly. You cut out, tells the computer, include all the plane waves up to this energy limit. If you set it too low, you are drawing with a fat marker. You'll completely miss the sharp details near the nucleus, and your physics will be wrong.
But if you set it too high, You're using an atomic microscope to draw the background sky. You're just wasting computational power on details you don't need.
Precisely. Now, we use a trick to avoid needing an insanely high cutoff energy. Because the core of an atom, the nucleus and the inner electrons, is really, really spiky. It's incredibly hard to draw accurately with plane waves.
And this is the pseudopotential.
Yes. We cheat. We say, you know what? The electrons deep inside the atom don't really do any chemistry. They just sit there shielded. So let's replace them. We replace the nucleus and those core electrons with a pseudopotential, a fake, smoothed-out potential. From the outside, it looks just like the real atom, but on the inside, all the sharp spikes are smoothed over.
So we don't need that superfine point pen anymore. We can get away with a reasonable cutoff energy and still get the right chemistry for the outer electrons, the valence electrons, which are the ones we actually care about.
Exactly. It saves us a massive amount of computer time. It's one of the key enabling technologies of practical DFT.
Okay, so we have built our solid, we converged our copoints and our cutoff energy.
Yeah.
We have a perfect infinite crystal. But usually, the interesting stuff, the chemistry, happens where the material interacts with the world. And that interaction happens at the surface.
Now, this is segment 3, surfaces and interfaces. Chapter 4, this is where the action is. Rust happens at the surface. Catalytic converters work at the surface. Computer chips are all about interfaces between surfaces.
But we have a problem. Our DFT code is built on the assumption that everything is infinite and periodic. It used that Pac-Man universe. So how do you create a surface and end to the material in a universe that loops around forever?
It is a bit of a hack, a very clever hack. We use the slab model.
Okay, walk us through that.
So you want to model the surface of copper. You take a few layers of copper atoms, say 5 layers thick, that's your slab. But then, inside your supercell, your repeating box, you add a large region of empty space on top of it. Vacuum.
So your box contains copper, 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 copper.
Yeah.
And then vacuum, 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 vacuum.
Right. Now, when the periodic boundary conditions kick in and repeat that box infinitely in the up-down direction, what do you get? You get an infinite stack of slabs floating in space, separated by gaps of vacuum.
And if the vacuum gap is wide enough, the flaps don't see each other.
Exactly. The electrons at the top surface of one slab don't interact with the bottom surface of the slab above it. So mathematically, you have created a true isolated surface.
But those surfaces must be incredibly unhappy places, chemically speaking.
Unhappy is the right word. Think about an atom deep inside a crystal. It's surrounded by neighbors on all sides. It's cozy. All its chemical bonds are satisfied. Now you slice that crystal in half. Suddenly the atoms on the new surface have lost half their neighbors.
They're exposed. They have these dangling bonds.
Exactly. This is a high-energy, unstable state. And since nature hates high energy, the surface atoms immediately try to fix it. The first and simplest thing they do is relaxation. They usually sink inward a little bit toward the bulk, trying to get closer to the neighbors they have left.
But sometimes they do something much more dramatic. The book calls it reconstruction.
Oh, yes. The silicon 100 surface is the most famous example of this. If you cut silicon along that particular crystal plane, every surface atom is left with 2 dangling bonds. It is wildly unstable. If you just modeled it as a perfect clean cut, your simulation would be garbage.
So what does the silicon actually do in reality?
The surface atoms physically move toward each other and bond with their neighbors on the surface. They form pairs, or dimers.
Like holding hands with the person next to you in line.
Exactly like holding hands. The whole surface reorganizes into these neat rows of dimers. This reconstruction completely changes the geometry and, more importantly, the electronic properties of the surface. And what's amazing is that DFT can predict this. You just set up the slab, tell the code minimize energy, and the atoms will automatically snap into these dimer rows.
And once we have a stable surface, we can start putting things on it. Absorption. This is the heart of catalysis, isn't it?
It is. Let's say you want to design a catalytic converter to turn dangerous carbon monoxide, CO, into safe CO2. You need a metal surface-like platinum to grab the CO molecule and hold it in place while an oxygen atom comes along to react with it.
But it can't hold it too tight or it gets stuck.
Right. This is the famous Sabatier principle. It's a Goldilocks rule. If the metal surface holds the molecule too weakly, it just flies off before it has a chance to react. If it holds it too strongly, the molecule gets stuck, it poisons the catalyst, and never leaves, blocking the site for the next reaction.
And DFT allows us to calculate that binding energy with pretty good accuracy.
We can screen thousands of potential metal alloys on the computer to find the one that has the perfect grip strength. We can design the catalyst atom by atom before ever setting foot in a lab.
Okay, so far we have been talking about statues, atoms that are frozen in place.
Okay.
We minimize the energy to find their lowest energy positions. But in reality, atoms aren't statues, they jiggle.
They never stop jiggling, even at absolute zero, which is a weird thought.
This brings us to segment 4, moving atoms. We're talking vibrations and kinetics, chapters 5 and 6. How does DFT handle the wiggles?
We go back to first-year physics. Think of a chemical bond as a simple spring connecting two heavy balls. If you pull the balls apart and let go, they'll vibrate back and forth.
And the frequency of that vibration depends on how stiff the spring is.
Exactly. Stiff spring, high frequency. Loose spring, low frequency. In DFT, we can numerically measure the stiffness of that spring. We take an atom, we nudge it a tiny bit, maybe 0.01 angstroms in the x direction, and we calculate the force that's pushing it back to its original spot.
And you do this for every atom in every direction. That sounds tedious.
It is, computationally. This process builds a massive table of numbers called the Hessian matrix. It sounds terrifying, but it's really just a complete map of all the spring constants between every pair of atoms in the system. Once you have the Hessian, you can calculate the phonons.
And phonons are the collective waves of vibration that travel through the crystal.
Right, and this brings up a really weird, purely quantum ghost story, zero-point energy.
0-point energy.
In classical mechanics, if you cool a system down to absolute 0 Kelvin, all motion stops. The atoms sit perfectly still at the bottom of their energy wells. But quantum mechanics says, no. Heisenberg's uncertainty principle says you can never know both the position and the momentum of a particle perfectly at the same time. If an atom stopped completely, you would know its exact position and that it had exactly zero momentum. That's forbidden.
So even at absolute 0, they have to keep vibrating.
They have to keep vibrating with this minimum amount of energy, the 0-point energy. And for light atoms like hydrogen, this energy is actually huge. It can be the difference between a reaction happening or not. If you run a high-precision DFT calculation and forget to add the 0-point energy correction at the end, your answer might be physically wrong.
Okay, so that's wiggling in place.
Right.
But what about moving from point A to point B? I'm talking about chemical reactions.
Kinetics. This is a huge area. Thermodynamics tells you if the reaction wants to happen. Is the destination lower in energy? But kinetics tells you how fast it happens. For example, thermodynamically, diamonds want to turn into graphite. Graphite is the lower energy state of carbon.
But my wife's diamond ring is not turning into pencil lead on her finger.
Because the kinetics are incredibly slow, it would take millions of years. To understand why, we need to use transition state theory.
And the book uses a great mountain pass analogy here.
It's the best way to think about it. Picture a hiking trip. You are in a valley. That's the reactant valley, your diamond. You want to get to the next valley over the product valley, your graphite. And between them is a big mountain range.
You're not going to hike straight over the highest peak. You're going to look for the lowest, easiest pass through the mountains.
Exactly. You want the path of least resistance. The highest point on that lowest path is the transition state. It's also called a saddle point.
Why a saddle?
Think of a horse saddle. From front to back, along the horse's spine, it curves up to a high point. But from side to side, it curves down. The transition state is just like that. It's an energy maximum along the path of the reaction. You have to climb up to it. But it's an energy minimum in all other directions. If you step off the path, you fall back down.
And the height of that pass, the energy barrier, determines the speed of the reaction.
High barrier. The reaction is slow. Low barrier. The reaction is fast.
But finding this saddle point must be mathematically tricky. If you just tell the computer minimize energy, it will just roll back down into the reactant valley. It won't stay balanced on top of the pass.
Correct. You absolutely cannot find a transition state by simple energy minimization. You need a different, more clever algorithm. And the most popular one, which the book details, is the nudged elastic band method, or NEB.
I love the visual for this one.
It's great. Imagine a string of pearls. One end of the string is anchored in the reactant valley. The other end is anchored in the product valley. The pearls are strung out across the mountains, representing a guess of the reaction path.
And the elastic band part.
There are virtual springs connecting the pearls to each other. These springs keep the pearls evenly spaced so they don't all just slide down into the valleys. Now you let the whole string relax. Gravity, or in our case, the atomic forces, pulls the pearls down, but the springs keep them stretched out. The string naturally settles into the lowest possible path over the mountains.
And the single pearl sitting at the very highest point of that relaxed path.
That is your transition state. That gives you the barrier height. And from that, you can calculate the reaction rate. It's an incredibly powerful technique.
We are getting deeper and deeper here. We have structures, surfaces, vibrations, and now reaction rates. But there's a huge elephant in the room that we need to address in segment 5. DFT, as we've discussed it, is a zero Kelvin, zero pressure theory.
It is. It models a perfect system of atoms in a vacuum at absolute zero. But we don't live in a vacuum at absolute zero. We live in a messy world with temperature and pressure.
So how do we bridge that gap? Chapter 7, 8, and 9 cover this area: thermodynamics, electronics, and dynamics.
We use a field called ab initio thermodynamics. What we do is take the raw DFT energies, which are internal energies at 0K, and we add the contributions from entropy, specifically vibrational entropy.
Those phonons, the wiggles we calculated earlier.
Exactly. The frequencies of those vibrations change with temperature. By using statistical mechanics, we can calculate exactly how much thermal energy those vibrations contribute to the system at 300 Kelvin or 1,000 Kelvin. We can also account for the pressure of a surrounding gas using things like the ideal gas law.
So we can actually predict things like phase diagrams.
Yes. We can create a map that says, okay, at room temperature and low oxygen pressure, this copper surface stays clean and metallic. But if we heat it to 500 degrees at a higher oxygen pressure, it will spontaneously form a copper oxide layer. We can predict corrosion or synthesis conditions without ever running a single experiment.
Let's shift to electronics, Chapter 8. Because sometimes we don't care about where the atoms are, we care about where the electricity goes.
Right. Conductors, semiconductors, insulators. To understand this, we have to look at a concept called the density of states, or DOS.
I like the stadium analogy for this.
It's perfect. Think of the available energy levels in a material as rows of seats in a giant stadium. The density of states is a chart that simply tells you how many seats are available in this particular row. Some rows might have lots of seats, some might have very few.
And the electrons are the spectators filling the stadium.
And they are very well-behaved spectators. They fill the seats from the field up. They take the lowest energy seats first. The energy level of the very last filled seat is called the Fermi energy. You can think of it as the sea level of the electron ocean.
So how does this tell us if a material conducts electricity?
You just have to look at the seats, right above the waterline, right above the Fermi energy. Are there empty seats available right there? If yes, then it's very easy for an electron to get a tiny kick of energy, hop up into an empty seat, and start moving around. That movement is electricity. That material is a metal.
But what if there's a big gap? What if the first empty row is way up in the nosebleed section?
That gap is a band gap. An electron needs a huge kick of energy to make that jump. If it can't make the jump, it can't move. That material is an insulator, or, if the gap is smaller, a semiconductor.
Now, we have to address a bit of a scandal. The book is very honest about this. Standard DFT is actually pretty bad at predicting these band gaps.
It is notoriously bad. It consistently and systematically underestimates them. For example, if you model silicon or germanium with a standard DFT functional like GGA, it might tell you the band gap is 0.
It says a semiconductor is a metal.
Yes.
Yeah.
Which is a catastrophic failure if you are trying to design a new solar cell material or a computer chip.
Why does it fail so badly at this one thing?
It comes back to that exchange correlation functional we talked about at the very beginning. The standard approximations, LDA and GGA, are based on the ground state density. They aren't really designed to handle the excited states that are involved in moving an electron across a gap. It's a fundamental flaw in the simplest approximations.
So if you need accurate band gaps, you need a better, more expensive functional. Which leads us perfectly into the final segment, accuracy in the future. Chapter 10.
This is the consumer reports section of the book. You have to ask, is the car I'm driving reliable? Sholl and Steckel break accuracy down into 2 types, which is a really useful distinction. Numerical accuracy and physical accuracy.
Numerical accuracy is basically, they do the math right.
Right. Did you use enough K points? Was your cutoff energy high enough? Was your vacuum slab thick enough to separate the surfaces? These are all solvable problems. If you were unsure, you just increase the settings and run it again. If the answer changes, you weren't converged.
But physical accuracy is the deeper, more difficult beast.
Physical accuracy asks, is the underlying equation itself actually describing reality? Even if you have infinite pay points and a supercomputer the size of the moon, you are still using an approximation for that exchange correlation functional. Is your approximation a good one for your specific problem?
And this brings us to the most beautiful metaphor in the entire field, Jacob's ladder.
John Purdue, who is one of the giants of DFT, coined this. He imagines a ladder reaching from Earth, representing crude approximations all the way up to heaven, which represents the exact perfect functional.
Let's climb the ladder. Rung 1 is Earth. That's LDA.
Local density approximation. Just looking at the density at a single point. It's sitting on the ground. Good for simple metals, but pretty bad for almost everything else.
Rung 2, this is GGA.
Generalized gradient approximation, we've added the slope of the density. This is where we live for 80% of materials science. It's a huge improvement over LDA. It gets things like bond lengths and structures mostly right. Rung 3. Meta GGA. This adds another piece of information. The kinetic energy density, which is related to the curvature of the density. It's getting more accurate, but the math is also getting hairier and the calculations are slower.
Rung 4, hybrid functionals.
Hybrids are a really big deal. They are a different philosophy. They mix a certain percentage of DFT with a bit of exact exchange from the older, more traditional Hartree-Fock method. Remember the band gap scandal?
Of course.
Hybrids often fix it. They open up that band gap to be much closer to the experimental value. They also predict reaction barriers much more accurately than GGAs. But the downside is they are 10 to 100 times more computationally expensive.
And rung 5 is heaven.
Chemical accuracy. The exact functional. We aren't there yet. That's the holy grail everyone is still searching for.
Before we wrap up, we need to warn the listeners about the two big potholes on the road, where standard DFT, like a rung 2 GGA, almost always breaks an axle. Pothole number 1, dispersion.
Van der Waals forces. These are the weak, long-range, attractive forces that hold layers of graphite together, or make water a liquid, or hold the two strands of DNA together. They arise from long-range correlations. If my electron moves here, your electron moves over there, across a significant distance. Standard DFT is very nearsighted. It only sees its local neighbors. It completely misses van der Waals forces.
So if you simulate graphite with a standard GGA functional,
the layers will just float away from each other. The calculation will say they don't bind at all, which is obviously wrong.
how do we fix that?
We use something called DFTD. The DFTD stands for dispersion. We basically paste a classical physics-based correction term onto the final energy that pulls the atoms together with the correct force. It's a bit of a patch, but it works surprisingly well.
Okay, pothole number 2, self-interaction error.
This is a weird one. In the math of standard DFT, an electron interacts with the total electron density. But that electron is part of the total density. So effectively, the electron interacts with itself. It repels its own density.
Like a ghost being afraid of its own shadow.
Exactly. In a normal metal like copper, the electrons are very spread out. They're delocalized, so this error kind of smears out and isn't a huge problem. But in materials like transition metal oxides, think of rust, or the materials in a lithium-ion battery cathode, the electrons are supposed to be sitting tightly on specific atoms. This self-repulsion pushes them apart artificially. It makes the material look more metallic than it really is.
And the fix for that?
DFT plus U. We add a penalty term, the Hubbard U, that basically forces the electrons to sit down and localize on the atoms where they belong. It's a way of canceling out that artificial self-repulsion.
So we have covered a massive amount of ground. I mean, we went from the impossible Schrödinger equation to the clever Kohn-Sham hack. We built infinite crystals, sliced them into surfaces, watched them vibrate, and hiked over energy mountains.
It really is a remarkable journey, and the book does such a good job of laying it out. We have turned quantum mechanics from a kind of abstract philosophy into a practical, predictive engineering tool.
So for the listener who has followed along and now wants to start driving this car, what's the key advice?
Sholl and Steckel offer great practical advice in their final chapter. First, benchmark. Don't just trust the code and the functional blindly. If you are studying a new material, calculate something known about it first. Calculate the lattice constant of copper. Does your result match the textbook value? If not, you need to check your settings.
Trust, but verify.
Second, know your functional. Don't just use the default PBE, a common GGA, because everyone else does. Ask yourself, does my system have important van der Waals forces? Do I need DFTD? Do I have transition metals with localized electrons? Do I need DFT plus U? The tool is only as good as the person using it.
Or finally, I guess, keep an eye on the future.
Absolutely. The ladder is still being built. People are developing better functionals every year, and computers are getting faster, which allows us to use those more accurate but expensive hybrid functionals more often. We are truly entering an era where we can design materials, new superconductors, new catalysts, new drugs, completely in silico on a computer before we ever mix a single chemical in the lab.
We're exploring the universe from a computer terminal. It's an amazing thought. A huge thanks to Sholl and Steckel for writing the guidebook, and thanks to you for breaking it all down for us.
My pleasure. It was fun.
Keep those electrons flowing, always check your convergence, and we will see you on the next deep dive.